energy level. They're on the same shell, what we would say, okay? We know this to be different other than hydrogen, and that's because as I add more electrons, I'm also going to have more electron repulsion. So as I increase number of electrons, the electrons should start to repel each other more and more and more. And that's why I see separation in terms of energy for these different orbitals, okay? So because of that, they're no longer going to be degenerate. So that means they're no longer on that same kind of even energy level. So if we think about in terms of energy, 1s is going to be my lowest in energy, so that will be closest to the nucleus. Then I'm at 2s, 2p, 3s, 3p, 4s, 3d, 4p, all of that, okay? So again, it's degenerate if we're talking about all on the same shell. So 3s, 3p, 3d are technically, since they're orbitals in a subshell and they have the same energy level, we would call them to be degenerate just because their energy level is the same. Energy level is a 3. But as we're writing in terms of repulsion and electron configuration, we're going to stack that energy up like this. Okay, so just kind of talking a little bit more about orbitals. S orbital, like we said, is spherical in shape, and the L value for my angular momentum number is going to be 0. So if ever I see L is equal to 0, that tells me immediately it's in the S orbital, or S shape, spherical. So it says the radius of the sphere increases with the value of n, meaning that as I add energy levels, that electron density is going to get larger and larger and larger, okay? Let's talk about something called a radial distribution or radial probabilities. So these are radial distribution graphs, these 3 right here. And ultimately, it's just a graph that shows the probability of us finding an electron versus the distance from the nucleus. So I have the probability of finding an electron, and that's going to be graphed next to how close that electron is by the nucleus. So if this first graph is just representing the 1s orbital, so this is just for s orbitals right now, I see that the distance that these electrons will be towards the nucleus is going to be pretty close. So I have a really high probability of finding an electron pretty close to the nucleus if I'm talking about the 1s orbital. That's how I would read this radial distribution graph, okay? If I start to add more of these s orbitals, so in the second graph, here's going to be my 1s orbital, now here's my 2s orbital. So now I have 1s, 2s, okay? There's a word here, it says node. A node is a region where there is 0 probability of finding an electron. And that means, think about, let's go back and think about these, go back to our analogy of the staircase. I can't just have electrons that are floating or that are traveling around in some type of just, without some type of designated space or without some type of orbital. So a node is representing that there's no particular shape or electrons are not going to be traveling in that designated area. It has to be in this spherical 1s, or it should be within this spherical 2s distribution, okay? So nodes are just representing that I have 0 probability of finding an electron. So here, once I get 2s that's added in here, I see that the distance from the nucleus is now much further because now I've added on another energy level. So since that electron had to have gained some amount of energy to stay farther away from the nucleus, so weaker Coulombic attraction, I'm going to see a larger distance here from the nucleus. I add another one, let's add the 3s, and now I see that my distribution is becoming even more spread out. Okay, so these are just radial distributions, and it's just really nice for us to see. It's just a way for us to chart where we can find an electron based on distance from the nucleus as we continue to add more energy levels, okay? And again, that's called radial distributions. Oh, and it's right here, so look at that. So radial distribution. Probability of finding an electron versus the distance that electron is from the nucleus. So I have 1s, 2s, 3s here. Okay, p orbitals, we know that the value for L for p orbital is 1. They have 2 lobes, which means that there's going to be a node right there in the origin. And when I say a node, that means that we're not going to be able to find electrons. I have 0 probability of finding an electron there. But I have 0 probability of finding it there because guess what's there probably in the middle? The nucleus, so that should make sense. And also they're dumbbell in shape. So we said before that the p orbital has there's 3 different p orbitals, and that's because they have 3 different orientations. I could have a p orbital along the z-axis, a p orbital along the x-axis, or a p orbital along the y-axis. So it's just the way I can orient that dumbbell in 3D space. D orbitals, we said the value of L for the d orbital is 2. I have 5 different types of orientations. 4 of them resemble a clover leaf in shape. So that's why we say they're clover leaf. But then we have this really weird random one that does not fit around. It looks like there's a p orbital with a donut around it. And that one's just crazy. Okay. So I can also have a radial distribution of comparing 2p, 3p, and 3d. So if I use instrumentation, we actually see that 3d is a little bit lower in energy than 3p. Okay, our last 4th quantum number, and then I swear we'll stop. Our last quantum number is called spin quantum number. And in spin quantum number, ultimately, an electron has to have some type of spin, meaning that it's going to have some type of movement to it. So in the 1920s, we figured out that 2 electrons in the same orbital do not have exactly the same energy. So we call this a spin because they don't have the same energy. Ultimately, what happened, I have some type of beam of atoms that are coming through this slit. So ultimately, my goal is to just get this to be a nice, either just one type of wave or just a stream of particles that's about to go through this magnet. And then I'm going to collect them. And what I found was, after it goes through the magnet, it splits. I have half of them being deflected this way, and I have another half of them being deflected in the opposite direction. So for us, that meant some of them have to have a spin in a positive direction, and some of these electrons are going to have a spin in a negative direction, or in the opposite direction. So for that spin quantum number, which we'll designate as m sub s, our spins are always going to be a positive 1/2 or a negative 1/2. So whenever you do your orbital diagrams and you're drawing your arrows to reflect the electrons, the reason that we draw one up and one down is because we need to show that the electrons have different spins. So an electron could have a positive 1/2 or a negative 1/2, and that will be its spin. Okay, we're going to pick up here tomorrow. So at the beginning of class, I want to build some of these models to see actually what it will look like when we layer orbital on orbital on orbital, okay? And we'll go at least to I think we'll go to 2p or 3p, I'm not sure. But I want us to actually see that so you can kind of get a better idea. And then we'll keep going with a little bit of this just because I want to do some practice with quantum numbers. And then towards the last half of class, we're going to do flame tests, okay? So make sure you wear closed-toed shoes. I will see you all tomorrow, and have a great night. Bye.